So I want to start this lecture by playing a game with you. It is a very simple game. It is a game you learn to play when you are 3 years old, sitting on the carpet with your wooden blocks. It is called counting. You put down a block and you say 1. You put down another block and you say 2. You put down another and you say 3. It seems like the most innocent thing in the world. It seems safe. It seems logical. But hidden inside this simple game is a trap. A trap that is going to destroy your common sense and break the machinery of your brain. Because when you learn to count, you learned a rule. Maybe nobody told you the rule explicitly, but you figured it out. The rule is called n+1. It means that no matter what number you give me, I can always add 1 to it and give you a bigger number. If you give me 1 million, I say 1,000,001. If you give me 1 billion, I say 1,000,000,001. If you give me the number of grains of sand in the Sahara Desert, I add 1 grain of sand and I beat you. This rule implies a promise. It promises that the game never ends. It promises that the road of numbers goes on forever. And because we have this rule in our heads, we invented a word for the end of the road. We call it infinity. We draw it as a symbol, a figure 8 tipped over on its side. And here is where the trouble begins. You think you know what that symbol means. You think it means a really big number. You think of it as a number that is just bigger than all the other numbers. And I am here to tell you that you are wrong. Infinity is not a number. It is not a place. It is not a thing you can put it in a bucket. And to prove this to you, I want to ask you a question about the real world. Can you have an infinite number of apples? Now you might sit there and say, well, Professor, theoretically, yes. And I say no, not theoretically, not practically, not at all. Because if you had an infinite number of apples, you would have an infinite amount of mass. And we know from the laws of gravity that mass attracts mass. If you fill the universe with infinite apples, the gravity would become infinite. The universe would instantly collapse into a black hole of infinite density. The laws of physics do not allow actual physical infinity. You cannot have infinite energy. You cannot have infinite time because the sun will burn out and the stars will die. You cannot have infinite space because the universe is expanding and has a horizon. So we have a strange situation. We have a concept in our heads called infinity, but we have a universe that is finite. We did not find infinity in the woods. We did not dig it up out of the ground. We built it. It is a mental construction. It is a ghost. But you say, Professor Feynman, who cares? It is just a useful idea. It helps us do math. But does it? Let us try to do some math with this ghost. Let us try to treat infinity like a number. Imagine I have a bag of gold coins, and let us imagine I am a magician, so I have an infinite number of gold coins in my bag. Now I take out 1 coin and I give it to you. How many coins do I have left? In normal arithmetic, if I have 10 and I give you 1, I have 9. The number gets smaller. But if I have infinity and I subtract 1, what do I have? I still have infinity. I have exactly the same amount of money as I started with. That is crazy. It violates everything you know about the world. It means that taking something away changes nothing. Now let us make it worse. Suppose I give you half of my gold coins. I give you all the ODD numbered coins, coin number 1 and coin number 3 and coin number 5. I keep the even numbers, coin 2 and coin 4 and coin 6. You have an infinite pile of coins and I have an infinite pile of coins. But wait, I started with 1 pile. Now I have 2 piles, and each pile is exactly the same size as the original pile. I have created money out of thin air. I have doubled my fortune by giving half of it away. This is why I say infinity is a monster. It does not obey the rules. It eats the rules. If you try to put infinity into an equation, it usually blows the equation up, and that creates nonsense. In physics, when we calculate something and the answer comes out to infinity, we do not say, aha, we have discovered something huge. We say, oh no, we made a mistake. We say the theory is broken. But the real terror, the real cliffhanger that keeps mathematicians awake at night is not adding or multiplying. It is subtraction. I want you to think about this question very carefully. We agreed that infinity plus 1 is infinity. We agreed that infinity divided by 2 is infinity. But what is infinity minus infinity? Imagine I have my infinite bag of coin, and you have your infinite bag of coin, and we take my bag and we subtract your bag. What is the answer? Is it 0, because they are the same size? Or is it infinity, because maybe my bag is a bigger infinity than yours? Or is it the number 7? The answer is that we do not know. The answer is undefined. The machine stops working. The gears grind together and the smoke comes out. When you pit one infinity against another infinity, common sense leaves the building. And to answer that question, to figure out what happens when monsters fight each other, we have to leave the world of apples and coins. We have to go back to ancient Greece. And we have to talk to a man who tried to prove that movement itself is impossible. We have to talk about the paradox of Zeno. Now I want you to watch me very closely. I'm going to do something that you think is completely normal. I am going to walk from this side of the stage over to that wall. Look, I am walking. I am moving. I have arrived at the wall. You say, Professor Feynman, that is not a physics experiment, that is just walking. But 2,500 years ago, there was a Greek fellow named Zeno who looked at what I just did, and he said, it is impossible. He said that motion is an illusion. He said that nothing in the universe can ever move from one place to another. Now, Zeno was not stupid. He was very smart, and he had a logical argument that is so powerful that it bothered mathematicians for 2,000 years. It is called the dichotomy paradox, and it goes like this. Imagine I want to walk to the wall. The wall is 10 feet away. Before I can get all the way to the wall, I first have to get halfway to the wall. That is obvious, right? I have to walk 5 feet before I can walk 10 feet. So I walk to the halfway point. Now I am standing there. I have 5 feet left to go. But before I can go the rest of the way, I have to go halfway of the remaining distance. I have to go 2.5 feet. So I do that. Now I have 2.5 feet left. But before I can finish, I must again go halfway of that distance, 1.25 feet. And then I must go halfway of that and halfway of that. Do you see the problem? I can keep dividing the distance by 2 forever. I can take the number 10 and divide it by 2, then divide by 2 again, then divide by 2 again. I can do that an infinite number of times. So you cannot walk an infinite number of steps. Therefore, you can never reach the wall. Therefore, movement is a leap. Now you're sitting there and you're laughing because you know I can't reach the wall. You saw me do it. So who is right? Is your eye right? Or is the logic right? This is a war between mathematics and reality. For a long time, the mathematicians were sweating. They were very embarrassed. They did not know how to answer Zeno. Then in the 1600s, we invented a new kind of math called calculus. Isaac Newton and Gottfried Leibniz came along and they found a trick. They looked at the series of numbers, 1/2 plus 1/4 plus 1/8 plus 1/16. And they said, yes, the list of numbers is infinite. You never stop adding. But the numbers you are adding get smaller and smaller and smaller. They shrink very fast. And if they shrink, fast enough, the total sum does not go to infinity. The total sum hits a wall. It hits a limit. If you take a pizza and you cut it in half, then you cut the half in half, then you cut that piece in half, and you keep piling up the pieces. You will never have more than one pizza. So the mathematician said, aha, we have solved it. An infinite number of steps can add up to a finite distance. 1/2 plus 1/4 plus 1/8 plus 1/16 equals exactly 1. So they told Zeno to go home. They said, calculus proves that motion is possible because infinite tiny things can create one finite big thing. Problem solved, right? Wrong. Because there is a hidden assumption in calculus. And there is a hidden assumption in Zeno's argument. They both assume that space is smooth. They assume that you can divide distance forever. They assume that between here and the wall, there is a continuous smear of space that can be cut into smaller and smaller slices without limit. But is that true? Is the physical universe actually smooth? Or is the universe chunky? We have a theory today called quantum mechanics, and it suggests something very disturbing about reality. It suggests that there might be a smallest possible distance. We call it the Planck length. It is a very tiny number. If you took a grain of sand and magnified it until it was the size of the universe, the Planck length would still be microscopic. But it is not zero. If the universe is made of pixels, if space is made of little tiny blocks, then Zeno is wrong for a completely different reason. He is wrong because eventually you get to a distance that you cannot cut in half. You get to the smallest pixel of space, and at that point, you cannot move halfway. You have to jump. You are at pixel A. And then suddenly you are at pixel B. You do not pass through the space in between because there is no space in between. So movement is not a smooth glide. Movement is a series of billions and billions of tiny teleportations from one pixel to the next. So we are left with a deep mystery. If space is smooth, then Zeno is right, and we need the magic of calculus to explain why we can move. If space is chunky, then Zeno is wrong, but we have to accept that we live in a video game made of pixels. We still do not know which one is true. We are still arguing about it. But Zeno was dealing with dividing things. He was dealing with the small. Now I want to take you in the other direction. I want to talk about the big. I want to talk about what happens when we try to pack things into boxes. And to do that, we have to leave the real world completely. We have to visit a very strange building, a building that has no end. We have to check into the Grand Hotel. Now I want you to take a trip with me. We are going to leave the real world behind. We are going to leave the world of Zeno and his atoms and his pixels. The real world is too messy. It has too many rules. We are going to go to a place that exists only in the mind of a mathematician. We are going to visit a hotel. But this is not a normal hotel like the ones in New York or London. In a normal hotel, you have a certain number of rooms. Maybe you have 100 rooms. Maybe you have 500 rooms. And if every room has a guest inside and a new person walks in the door, the manager has to say, I am sorry, sir, but there is no vacancy. Go away. We are full. That is how finite numbers work. If a bucket is full, you cannot put more water in it. But the hotel I want to take you to is different. We call it the Grand Hotel, or sometimes we call it Hilbert's Hotel, named after David Hilbert, who built it in his imagination. This hotel has an infinite number of rooms. Room number 1, room number 2, room number 3, on and on forever. There is no last room. Now, here is the situation. It is a busy weekend. The hotel is full. When I say full, I mean full. There is a guest in room 1. There is a guest in room 2. There is a guest in room 1,000,000. Every single room key has been handed out. There are no empty beds anywhere. So now imagine that a weary traveler walks in the front door. He walks up to the desk and he asks for a room. Now, in the real world, the manager would say no. But in the Grand Hotel, the manager smiles. He says, "No problem, sir. Wait 1 minute." He gets on the loudspeaker and he makes an announcement to the guests. He says, "Attention, please. I need every guest to move to the room number that is one higher than their current room. If you're in room 1, please move to room 2. If you're in room 2, please move to room 3. If you're in room 100, please move to room 101. We have a rule in mathematics. N goes to n plus 1. Now think about what happened. Does the person in the last room run out of space? No, because there is no last room. Every single person has a place to go. The line of rooms stretches out to infinity, so nobody falls off the edge. And what happens to room number 1? The guy who was in room 1 moved to room 2. So room number 1 is now empty. The manager gives the key for room 1 to the new guest. So look at what we just did. We started with a hotel that was completely full. We added one person, and we found a place for him without kicking anyone out. This tells us something very strange about infinity. It tells us that infinity plus 1 is equal to infinity. In normal life, if you add something, things get bigger. In the world of the infinite, adding something changes nothing. The size stays the same. But now, I want to make the headache worse. I want you to imagine that it is a holiday weekend, and suddenly a bus pulls up to the Grand Hotel. But this is not a normal bus. This is a magical bus. It is infinitely long. It has an infinite number of seats, and it is carrying an infinite number of passengers. So now we have a crisis. We have a full hotel, an infinite number of guests, and we have a full bus, an infinite number of new guests. We need to fit an infinity inside another infinity. We cannot use the trick we used before. If we move everyone up by one room, we free up room 1. That fits the first guy from the bus. And if we move everyone up again, we free up room 2. That fits the second guy. But that will take forever. We have an infinite line of people waiting. We cannot move them one at a time. We need to open up an infinite number of doors all at once. So what does the manager do? Does he give up? Does he tell the bus to go away? No, he is a mathematician. He knows how to cheat. He gets on the loudspeaker and he says, "Attention, guests. I need you to look at your room number. I need you to multiply your room number by 2, and please move to that room." Think about the arithmetic. The guy in room 1 moves to room 2. 1 multiplied by 2 is 2. The guy in room 2 moves to room 4. 2 multiplied by 2 is 4. The guy in room 3, he moves to room 6. The guy in room 1,000,000 moves to room 2,000,000. Is there room for everyone? Yeah. The even numbers go on forever. So all the old guests are safe. They are all sitting in the even-numbered rooms. But what about the ODD-numbered room? Room 1, empty. Room 3, empty. Room 5, empty. Because we moved everyone to the evens we have left. All the odd numbers completely vacant. And how many odd numbers are there? There are an infinite number of odd numbers. So we tell the people on the bus to file in. Person 1 goes to room 1. Person 2 goes to room 3. Person 3 goes to room 5. We have just fit an infinite number of new people into a hotel that was already full. And we did it by exploiting a property of numbers that breaks your common sense. We proved that the set of even numbers is exactly the same size as the set of all numbers. This is the madness of the Grand Hotel. It tells us that in the land of the infinite, the part is equal to the whole. You can take half of the infinity away and you still have the whole infinity left. So you might think, okay, Professor Feynman, I get it. Infinity is just a bottomless pit. You can throw anything into it and it never fills up. You might think that all infinities are the same, that infinite is just infinite, and that is the end of the story. But you would be wrong, because about 150 years ago, a man named Georg Cantor looked at this hotel and he asked a dangerous question. He asked, is it possible to build a bus so big that it cannot fit into the hotel? Is it possible to have an infinity that is bigger than the infinity of the counting numbers? And the answer he found shook the foundations of mathematics. Thus, it turns out that there are monsters bigger than the Grand Hotel. And to find them, we have to stop counting 1, 2, 3. We have to look at the decimals on Desia. So we have played with the hotel. We have moved the guests around. We have fit an infinite bus into an infinite lobby. And you might be thinking to yourself, well, Professor, that is just a parlor trick. That is just wordplay. You might think that infinity is just infinity, and that is all there is to it. But in the 1870s, a man named Georg Cantor decided to look this monster in the eye. He was a German mathematician, and I have to tell you, he was a very brave man, because at that time, talking about infinity as a real thing was forbidden. The other mathematicians hated it. They called him a charlatan. They called him a corrupter of youth. But Cantor did not care. He wanted to know the answer to a specific question. He wanted to know, is there a way to measure the size of an infinity? Now think about that. How do you measure something that has no end? You cannot use a ruler. You cannot count it because you will never finish counting. So Cantor had to invent a new way of comparing things, a way that does not involve counting. I call this the dance partner method. Imagine we are in a giant dance hall, and there is a crowd of boys standing on the left side, and there is a crowd of girls standing on the right side. And I want to know, are there more boys or are there more girls? Now I could try to count them one by one. 1, 2, 3, 4. But if the crowd is huge, it takes a long time and I might make a mistake. But there is a faster way. I tell them to pair up. I tell every boy to go grab the hand of one girl. If everyone has a partner and nobody is left standing alone, then I know for a fact that the number of boys is exactly equal to the number of girls. I do not need to know the number. I just need to know the match. We call this one-to-one correspondence. So Cantor took this idea and he applied it to numbers. He wanted to compare two specific sets of numbers. Set A is the natural numbers, the counting numbers, 1, 2, 3, 4, 5, and so on. Set B is the even numbers, 2, 4, 6, 8, 10, and so on. Now I want you to use your intuition. If I ask you which set is bigger, what does your gut tell you? Your gut tells you that set A is bigger. In fact, your common sense screams that set A is twice as big as set B. Why? Because the counting numbers contain all the evens plus all the odds. The evens are just half of the list. So obviously the whole must be bigger than the part. That is logic. That is sanity. But Cantor said, no. Watch the dance. Let us line them up. I take the number 1 from the first list. I tell it to dance with the number 2 from the second list. I take the number 2. I partner it with the number 4. I take the number 3. I partner it with the number 6. Do you see the rule? I take the number n and I match it with 2 multiplied by n. Now I ask you a question. Is there any counting number that does not have a partner? No. If you give me 1 billion, I match it with 2 billion. Is there any even number that is left alone? No. If you give me an even number, I just divide it by 2, and I find its partner in the first list. Every single number has a date for the dance. There are no leftovers. The lists are perfectly locked together, zipper tight. And because they matched perfectly, Cantor was forced to a conclusion that sounded completely insane. He concluded that the set of even numbers is the same size as the set of all numbers. This is what drove his critics crazy. It means that in the world of the infinite, size does not mean what you think it means. It means that you can take an infinite set, you can throw away half of it, you can throw away the odd numbers, and the thing you have left is exactly as big as the thing you started with. We call this cardinality. Cantor proved that the infinity of the counting numbers is a specific kind of infinity. He gave it a name. He called it a left null. So now we feel like we understand the game. We think, okay, Professor Feynman, I get it. All infinities are the same size. You can just match them up. You can match the integers to the evens. You can match the integers to the multiples of 10. You can even match the integers to the fractions. It seems like Aleph Null is the only game in town. It seems like infinity is just one big happy family where everyone is the same size. And for a while, Cantor thought so too. He thought that maybe every single infinite set in the universe could be lined up and counted. He thought that maybe infinity was just one single size. But then he looked at the decimal. He looked at the numbers between 0 and 1. 0.1, 0.01, 0.123, 45. And he asked himself, can I match these numbers to the counting numbers? Can I line them up? And when he tried to do it, he discovered something that terrified him. He discovered that the real numbers are not just infinite. They are a different kind of infinite. They are an infinity that is so big it swallows the other infinity whole. He found a way to break the machine. He found the diagonal slash. So we are feeling pretty good about ourselves. We have learned that the even numbers are the same size as the all numbers. We have learned that the fractions are the same size as the integers. We have this nice warm feeling that infinity is just one big bucket. You can label the bucket Aleph Null and everything fits inside it. But Georg Cantor was a troublemaker. He was not satisfied with the bucket. He started looking at the numbers between 0 and 1. I am talking about the decimals, the real number. 0.5, 0.3, 33, 0.14, 159. And he asked a very simple question. Can we put these numbers in a list? Can we play the dance partner game with the decimal? Remember the rule. If I can list them one by one, if I can say this is number 1 and this is number 2 and this is number 3, and if I can guarantee that I will eventually count every number on the list, then they are the same size as the counting numbers. So let us try. Let us try to make a master list of every possible decimal number. I want you to imagine a piece of paper that is infinitely long. On the first line, I write a number. Let us just make it up. Let us say 0.1, 2, 3, 4, 5. On the second line, I write another number, 0.55, 555. On the third line, I write 0.98765. And on the fourth line, I write 0.3, 0000. I fill the page. I write down an infinite list. And I claim to you that I have written down every single number that exists between 0 and 1. I claim that there are no numbers missing. My list is complete. Now Cantor looked at this list and he smiled. He said, Professor, I do not believe you. He said, I bet you that I can find a number that is not on your list. And I say, impossible. I wrote them all down. And he said, no, I'm going to manufacture a number. I'm going to build a number right in front of your eyes that is guaranteed to be missing. He does it using a trick we call the diagonal argument. Here's the recipe. He looks at the first number on my list, 0.123. 45. He looks at the first decimal digit. It is a 1. He says, I'm going to start my new number, but I'm going to make sure the first digit is different. If your digit is a 1, I will make my digit a 2. So his mystery number starts 0.2. Now he looks at the second number on my list, 0.5, 5, 5, 5, 5. He looks at the second decimal digit. It is a 5. He says, I am going to change it, and I will make my second digit C. So his mystery number is 0.26. Now he looks at the third number on my list. He looks at the third digit, and he changes it. Do you see what he is doing? He is walking down the diagonal. He has taken the nth digit of the nth number, and he is switching it. He does this forever. And when he is finished, he holds up this new number, this mystery number. And he asks me, is this number on your list? Let us check. Is it the first number on the list? No, it cannot be, because the first digit is different. We made sure of that. Is it the second number on the list? No, it cannot be, because the second digit is different. Is it the 1,000,000th number on the list? No, because the 1,000,000th digit is different. This mystery number is different from every single number on my infinite list by at least one digit. It is a ghost. It exists, but it's nowhere to be found on the page. And here's the kicker. I can take this new number and I can write it at the bottom of the list. I can say, okay, Cantor, you got me. I added it. Now the list is complete. And Cantor says, no, because I can do the diagonal trick again. I can make another number that is missing. And I can do it again and again. No matter how hard I try, no matter how many infinite years I spend writing, I can never list all the decimal numbers. There are simply too many of them. The crowd of decimals is too big to fit through the door of the counting numbers. This LED cantered to a conclusion that shattered mathematics. It proves that there are different sizes of infinity. There is the first size, the countable infinity, the size of the integers. This is the smallest infinity. And then there is the second size, the uncountable infinity, the size of the reals, the size of the continuum. And the second infinity is bigger than the first infinity. It is not just a little bit bigger. It is infinitely bigger. It is like comparing a cup of water to the Atlantic Ocean. The integers are infinite, but they are scattered like dust. The real numbers are continuous. They are solid. They are heavy. So now we know there is a hierarchy. We are not just dealing with one monster. We are dealing with a whole species of monster. Some are small and some are giant. And naturally, once you find a monster that is bigger than the first one, you have to ask the next question. Is there a monster bigger than that? Is there a biggest infinity? Or does the Tower of Terror go up forever? To answer that, we have to stop looking at numbers and we have to start looking at sets. We have to look at the power set. And that is where we find out that the rabbit hole has no bottom. So now we are in deep water. We have left the shore of common sense far behind. We found out that the integers are one size of infinity. We call it Aleph null. We found out that the decimals are a bigger size of infinity. We call it the continuum. So now you're sitting there and you're wondering, Professor Feynman, is that it? Are there just two sizes? Is it like shoes where you have small and large and that is the end of the catalog? And the answer is no. The answer is that there are infinitely many infinities. There is a ladder of giants that goes up forever. And the way we build this ladder is using a simple little tool called the power set. Now, do not let the name scare you. It is just a fancy name for making combination. Let us forget about infinity for a second. Let us look at something small. Imagine I have a bag, and inside it I have three colors: red, blue, green. That is my set. It has three things in it. The size is 3. Now I ask you a question. How many different combinations of colors can I make from this bag? Let us list them. I can pull out just red. I can pull out just blue. I can pull out just green. That is 3 combinations. I can pull out red and blue. I can pull out red and green. I can pull out blue and green. That is 3 more. So we are up to 6. I can pull out all of them. Red and blue and green, that is 7. And here's the one everybody forgets. I can reach in and pull out nothing, the empty set. That counts as a combination too. So that makes 8. We started with 3 elements, but we made 8 combinations. If we started with 4 elements, we would get 16 combinations. The formula is very simple. It is the number 2 raised to the power of the number of things. 2 multiplied by 2 multiplied by 2. And here is the crucial fact. Here is the thing you must remember. The number of combinations is always bigger than the number of original things. 8 is bigger than 3. 16 is bigger than 4. You can never match them up 1 to 1. There are always more groups than there are individuals. Now, if Cantor looked at this and he has said, what happens if I do this to the infinite set? Imagine a bag that holds all the integers. 1, 2, 3, 4, forever. That is aller null. That is the smallest infinity. Now let us make the set of all possible combinations of those numbers. A bag containing every possible group of numbers you can imagine. Logic tells us that this new bag must be bigger than the first bag. Just like 8 is bigger than 3. The power set of Aleph null is bigger than Aleph null. This new infinity is what gives us the decimal. It is the uncountable infinity. But Cantor did not stop there. He said, okay, I have this new giant infinity. What happens if I take the power set of that? What if I take the bag of all decimals and I make all possible combinations of decimal? Will the rules still hold? 2 raised to the power of a giant infinity creates a supergiant infinity. And then I can take the power set of that and the power set of that. Do you see the horror of it? It is an escalator. It is a tower. You start with the basement infinity. The integers. You step up to the 2nd floor, the reals. You step up to the 3rd floor, the set of all functions. You step up to the 4th floor, and there is no roof. There is no biggest number, and there is no biggest infinity. No matter how huge a monster you build, I can always come along and say 2 to the power of your monster, and I create a bigger monster that swallows yours whole. We call this the Beth hierarchy, Beth 1, Beth 2, Beth 3. It is dizzying. It means that the word infinite is almost meaningless because it is not specific enough. It is like saying the word number. Which number? Which infinity? There are an infinite number of different sizes of infinity, each one infinitely larger than the last. So now we are standing on top of this tower. We have built a mathematical structure that is so tall it pierces the sky. We have left the physical world completely behind. And this is where the trouble starts, because mathematics is a game we play in our heads. In our heads, we can do anything. We can build infinite hotels. We can build infinite towers. But eventually we have to wake up. We have to open our eyes and look at the real universe. We have to look at atoms. We have to look at electrons. We have to look at light. And we have to ask a very painful question. Does nature know about this tower? Does the electron care about Aleph null? Because when we try to take these beautiful infinite mathematics and we try to use them to describe the mass of a tiny particle, something terrible happens. The math that does not just get complicated. The math explodes. We are going to find out what happens when the irresistible force of infinity meets the immovable object of reality. We are going to find out why physicists had to cheat to save the universe. We have to talk about the disaster of quantum electrodynamics. So we have climbed the tower. We have seen the different sizes of infinity. We have played the games of the mathematicians. And it is a beautiful game. It is a wonderful game of logic. But now I have to be the party pooper because I am not a mathematician. I am a physicist. And my job is not to worry about what creates a beautiful logical structure. My job is to find out how nature behaves. And nature does not seem to care about our beautiful tower. In fact, when we try to bring this concept of infinity down from the clouds and apply it to the real dirt and rocks of the universe, we get into terrible trouble. We get into a disaster. I wanted to talk to you about the electron. It is a little fellow. It is the thing that carries electricity through the wires. It is the thing that buzzes around the nucleus of the atom. Now we have a very simple question, a question you would think we should be able to answer. How big is the electron? I do not mean how heavy is it. I mean, what is its radius? How much space does it take up? For a long time, we tried to measure it. We shot things at it to see if they bounced off a hard surface. Every time we looked, we found the same answer. The electron appears to be a point. It has no radius, it has no surface, it is 0 inches across, it is a mathematical dot. Now, you might say, okay, professor, so it is small. What is the big deal? The big deal is the electric field. You know that an electron has a charge. It pushes other electrons away, and the closer you get to the electron, the stronger that push becomes. We have a law for this. It is called Coulomb's law. It is very similar to gravity. The energy of that field is proportional to 1 divided by the distance from the center. Now use your arithmetic. If I stand 1 meter away, the energy is 1. If I stand 1 centimeter away, the energy is 100. If I stand 1 millimeter away, the energy is 1,000. But what happens if the electron is a point? What happens if I go all the way to the center? What happens when the distance is 0? 1 divided by 0 is infinity. This implies that the electron is sitting in the middle of a ball of infinite energy. And Einstein taught us that energy is mass. E equals mc squared. So if the electron has infinite energy, it must have infinite mass. It should weigh more than the sun. It should weigh more than the whole galaxy. A single electron should be a black hole that swallows the entire universe. But we measured the electron in the laboratory. We put it on a scale, and it is tiny. It is the lightest thing we know. It is 9.1 multiplied by 10 to the minus 31st kilogram. So we have a contradiction. The theory says infinity. The experiment says tiny. This is embarrassing. It is humiliating. For 50 years, physicists were stuck here. We calculated nonsense. And it gets worse. When we invented quantum mechanics, we thought maybe that would fix it. In quantum mechanics, the electron is not just sitting there. It is interacting with the world. It is emitting photons and absorbing them again. It is like a man throwing a ball up in the air and catching it. The electron emits a photon. That photon goes a little distance, and then the electron runs and catches it. We call this self-interaction. The electron is touching itself. When we try to calculate the energy of this interaction, we have to add up all the possible paths that photon could take. It could go a short distance, it could go a long distance, and it could go a microscopic distance. And when we sum up all those paths, guess what we get? Infinity. The math blows up in our faces again. So we have this monster. We have this infinity appearing in our equations for the most basic particle in the universe. So what did we do? Did we throw away the theory? No, we cheated. We invented a trick, a shell game. We call it renormalization. It works like this. We say, okay, the math gives us an infinity. But let us pretend that the measurement we make in the lab is not the real mass. Let us pretend that the electron has a bare mass, a secret, naked mass that we can never see. And let us assume that this naked mass is negative infinity. So we have the positive infinity from the interaction, and we have the negative infinity from the naked mass. And we simply choose the negative infinity so that it exactly cancels out the positive infinity and leaves behind the tiny little number we measure in the lab. Infinity minus infinity equals 9.1. Now you're laughing. You should be laughing. It sounds like hocus pocus. It sounds like sweeping the dirt under the rug. I have called it a Dippy process. I have said that I do not think it is mathematically legitimate. But, and this is the big but, it works. When we use this trick, we can calculate the behavior of the electron to 10 decimal places of accuracy. It is the most precise theory in the history of mankind. So nature is telling us something very subtle. She is telling us that maybe we are not supposed to go all the way to zero. Maybe the idea of a point is wrong. Maybe when you get down to the truly tiny scales, the Planck scale, the rules of space and time change. Maybe space gets chunky, and maybe it gets fuzzy. Maybe the distance never actually reaches zero, so the infinity never actually happened. Modern physicists think this is the answer. They think that our theories are only effective theories, and they work at the size of atoms, but they fail at the size of pixels. The infinity in our math is a warning sign. It is a sign that says, do not enter. It is a sign that says our understanding stops here. We have pushed our logic as far as it can go, and we have hit a wall. And this brings us to the final chapter of our story, because it is not just physics that has a problem with infinity. It turns out that logic itself has a hole in it. We used to think that if we were smart enough, we could prove everything. We thought that with enough time and enough paper, mathematics could solve every riddle. But then a man named Kurt Gödel came along and he proved that there are things that are true but can never be proven. He showed us that the tool of logic has a limit. We have to talk about the incompleteness theorems. We have to talk about the blind spot in the mind of God. So we have arrived at the final chapter. And I have to tell you that the situation is grave. We started this lecture thinking that infinity was just a game, just counting. Then we found out it breaks our common sense with the hotel. Then we found out it creates monsters of different sizes with the sets. Then we found out it breaks the laws of physics with the electron. But we still had one hope left. We still had the hope that at least logic was safe. We thought that even if the physical world is messy, and even if our brains are small, the rules of mathematics are perfect. We thought that mathematics was a machine made of diamond, pure solid, unbreakable. In the early 20th century, there was a very famous mathematician named David Hilbert, and he had a dream. He wanted to prove that mathematics is complete. He wanted to build a system where if you ask any question at all, like, is this equation solvable? Or is this number prime? You could turn the crank of the machine and eventually a ticket would pop out saying yes or no. He believed that there is no such thing as an unsolvable problem. He said, we must know and we will know. It was a beautiful dream, the dream of total knowledge. And then in the year 1931, a young man named Kurt Gödel walked into the room and he smashed that machine into 1,000,000 pieces. He did not use a hammer. He used infinity. And he used a trick of language called self-referent. Now, to understand this, I want you to look at a very simple sentence. This sentence is false. Think about that. If the sentence is true, then it says it is false, so it must be false. But if the sentence is false, then it is telling the truth, so it must be true. It is a loop. It is a paradox. It vibrates back and forth. True, false, false. Now, for a long time, mathematicians said, well, that is just a silly word game. That is just language. Mathematics does not do that. Mathematics deals with numbers. 1 + 1 = 2. There is no paradox there. But Gödel found a way to turn language into numbers. He invented a code. We call it Gödel numbering. He showed that you can take any statement of logic and you can turn it into a unique number. And because the list of numbers is infinite, he could create a statement that talks about itself. He built a mathematical equation that essentially says the following: this statement cannot be proven. Now, I want you to watch the logic very carefully, because this is the moment where the universe cracks open. We have two possibilities. Possibility one, the statement can be proven. If we can prove it, then the statement is false because it says it cannot be proven. But if we prove a false statement, then mathematics is broken. It means we can prove lies. It means the system is inconsistent. We do not want that. That is a disaster. So let us look at possibility two. Possibility two, the statement cannot be proven. Well, that is exactly what the statement says. So the statement is true. Do you see what just happened? We have found a statement that is absolutely true, but it has no proof. It sits there in the middle of mathematics. We know it is true. God knows it is true, but the rules of mathematics are not strong enough to reach it. This is called the first incompleteness theorem, and it tells us something terrifying. It tells us that in any logical system that includes the infinity of numbers, there will always be blind spot. There will always be truths that are outside the reach of logic. We are like a painter trying to paint the floor of a room while we are standing inside the room. We paint the corner. Over there, we paint the middle. But eventually, we paint ourselves into a corner. We cannot paint the spot where we are standing. To paint that spot, we have to step out of the room. We have to go to a bigger system, a bigger infinity. But if we step into the bigger room, we just have the same problem again. Now we have a bigger floor and a new blind spot where our feet are. No matter how big you make the system, no matter how many axioms you AD, there will always be things that are true but unprovable. This destroyed Hilbert's dream. It proved that we can never mechanize truth. We can never build a computer that can solve every problem, because there will always be a Gödel sentence that the computer cannot chew. This is the limit of knowledge. It is not a limit because we are stupid. It is not a limit because we do not have enough time. It is a limit built into the very structure of logic itself. The infinity of truth is bigger than the infinity of proof. We can feel the truth, we can see the truth, but we cannot always write down the steps to get there. So we have seen that infinity breaks our counting, it breaks our physics, and now it breaks our logic. So you might be feeling a little bit depressed. You might be thinking, Professor Feynman, if we cannot understand infinity, and if we cannot prove everything, then what is the point? Why are we even trying? And that brings me to the conclusion. Because I do not think this is a sad ending. I think it is a triumph. I think the fact that a biological machine made of meat and electricity, a machine that evolved to pick bananas and run away from tigers, the fact that this machine can look at the infinite and realize that it cannot be tamed, that is the miracle. We have found the edge of the map, and that is a place of wonder. So we come to the end of the road. We have been on a long journey today. We started with the blocks in the nursery. We counted 1, 2, 3. It felt safe. It felt solid. But then we pulled the thread. We visited the Grand Hotel and we saw that you can fit an infinite bus into a full building. That broke our common sense about space. We climbed the Tower of Sets with Cantor and we saw that there are infinities bigger than infinities. That broke our common sense about size. We looked at the electron and the laws of physics, and we saw that the math blows up and gives us nonsense answers. That broke our common sense about matter. And finally, we looked at logic itself with Kurt Gödel, and we saw that truth is bigger than proof. That broke our common sense about reason. So now you're probably sitting there with a headache. You are probably feeling a little bit dizzy. You might be feeling that mathematics is not the solid ground you thought it was. You might feel like you're floating in a void. And the question you have to ask is why? Why is this so hard? Why does the human brain crash like a broken computer whenever it tries to really understand infinity? The answer is actually very simple. It is not a mathematical answer. It is a biological answer. Look at where you came from. You are an animal. You are a biological machine made of meat and water and electricity. Your brain evolved over millions of years on the savannas of Africa. And what did that brain evolve to do? It evolved to find bananas. It evolved to run away from tigers. It evolved to find a mate. Now think about those problems. If you see a tiger, you need to know if there is one tiger or two tigers. If you see a banana, you need to know if there are 5 bananas or 10 bananas. You deal with finite numbers, small numbers, numbers that you can touch with your hands. Evolution never had any reason to build a brain that understands infinity. Infinity does not help you eat. Infinity does not help you survive. If you stand there contemplating the infinite nature of the grass, the lion eats you. So we are finite creatures. We have finite memories. We have a finite number of neurons firing in our heads. And yet we are trying to run software that is infinite. We are like a pocket calculator trying to run a simulation of the entire galaxy. Of course, the machine smokes. Of course, it glitches. We are trying to put the ocean inside a teacup. And this leads some people to say that infinity is not real. There is a movement in mathematics called finitism. They say, look, Professor Feynman, nature is finite. The brain is finite. Pixels are finite. They say that infinity is just a fiction, a mistake in our language. They say we should banish it. We should stop talking about it. They say we should only do math with numbers we can actually count. But I cannot agree with that. I think that is giving up, because look at what we did today. Yes, our brains are small. Yes, we are just monkeys with shoes on. But somehow we managed to find the edge of the cage. We used our finite logic to prove that logic has a limit. We used our finite physics to find the point where the laws break down. We looked into the dark and we mapped the monsters. And that is a tremendous thing. That is the glory of the human race. We are the only thing in the universe that is capable of thinking about things that are bigger than ourselves. We are a part of the universe that has woken up and started to ask questions about the whole. So when you go home tonight, I do not want you to be afraid of the monster. I do not want you to worry about the hotel or the diagonal slash. I want you to appreciate the miracle that you can even ask the question. The universe is strange. It is chunky at the bottom. It is fuzzy at the edges. It is full of holes where the logic falls through. It is not a clockwork machine. It is something much more wild. And we are just at the beginning of understanding it. We have learned that we cannot know everything. Gödel taught us that. But that does not mean we should stop trying. It means that the adventure will never end. It means there will always be a new mystery waiting around the corner. There will always be an N+1. And personally, I think that is a very good thing. because a game that never ends is the only game worth playing. Thank you very much.